Hey, welcome to another video. So in this video, man, we got an important one. We learned how to graph sine and cosine with some transformations in there. So we're going to learn what happens and when we adjust the period of sine and cosine. We're going to use that in tangent and cotangent, secant and cosecant later on, but it all starts right here. So here's what we're going to learn in this video. We're going to learn that when you start multiplying the inside, the argument of your trig functions, it's going to start adjusting your period. How often this repeats, either closer or further, that's a horizontal stretch or compression. We're going to learn what happens when you start multiplying the function right here in front of that function, how that affects the output in terms of its amplitude. We're going to learn how to shift this, and all these things are going to be very relevant and very much like if you've learned how I've taught you graphing previously with all of your transformations. The only thing we're not getting into right now is called a phase shift. So a phase shift is the horizontal transformation, the horizontal shift, left or right. And it's always opposite what's ever in that parentheses, and the same thing holds here. So what I intend to teach is the 4 steps on how to graph these trig functions. There's going to be 5 when we talk about a horizontal shift, a phase shift, but honestly it's not that bad. If you follow these steps, you're going to get it right like every single time, and I'm going to walk you through exactly how to do it. So here's the first thing. Whenever we look at how to graph sine and cosine, the following steps I need to be in your head. Number 1, I need you to find that period. So I'm going to show you exactly how to deal with that. Our period, we always write t for period, is 2 pi. Why 2 pi? Well, 2 pi because the original period of every sine and cosine function is 2 pi until we start manipulating that, stretching that, or compressing that. 2 pi divided by, we call it omega. It's this number that's right in front of x. When we get to phase shifting, I'm going to show you how that works a little bit more clearly if you have something added, subtracted. But for right now, it's just this number in front of x. So we take our period, 2 pi, and divide it by that omega. Now, think about this. What would it be for tangent? So tangent has a period of not 2 pi, has a period of pi. And so we'd have for tangent pi over omega. So please be clear on that, that this period is for sine and cosine, which is why I have it right here under that. We're going to find our period first. After that, we're going to identify any sort of vertical shift, plus up, minus down, with what's added or subtracted at the end of our function. And we're going to graph it in this order. We're going to first put our period down. We're going to put the end of our period, half our period, and quarters of our period. Why? Well, that's how I introduced graphing to you in the last video. Then we're going to show our shifting up or down. At that point, we'd show our shifts left or right as well, and then per period back there, but we're not there yet for phase shifting. Then we're going to mark our x-intercepts. Remember this, for sine, our x-intercepts happen at the ends and the center of our period. For cosine, it's at the quarters of our period. Finally, we'll take our key points, our peaks, at the quarters for sine, at the ends and center for cosine, and we'll use our A to multiply the outputs of those key points, and that'll give us a very, very clear graph. One thing is that letter A can do 2 things for you. It will cause you to stretch or compress, and it'll also cause you to reflect if it's negative. The absolute value of that A is called our amplitude, and it will give you how high you go above the x-axis and how low you go in terms of absolute value. So we can talk about that as well. The way I'm teaching, you generally don't need that exactly. Some textbooks do use it though. So let's get right to it. Let's talk about 3 sine x. I'm going to lead you through this as efficiently as possible. I'm going to give you the steps and show you exactly how and why we're doing that. Whenever you graph any sort of a trig function, the first thing you need is whatever the period is. So we're going to take the period, which is for sine, 2 pi. And we're going to divide that by whatever number is being multiplied by x. That's going to be 1 in this case. So 2 pi divided by 1 is 2 pi. Now, I'm not doing that just to bore us. I'm doing that to show you this is the process you take every time. You take the period of your trig function, you divide it by omega. That's the number in front of x, and whatever you get is your period. Stop right there. Don't do anything else. Put that period on your x-axis. So what I mean by that is, at this point, since we know that we have 2 pi as our period, we're going to go from 0. We're going to mark 2 pi. And you go, how do I know where 2 pi is? Who cares? It's not the scale anyway. Just put 2 pi on there somewhere. Now, Every important feature of sine and cosine happens at quarters, ends, and half of your period, which is why we're dealing with the period first. It will determine your key points for you in just a minute. So put the 2 pi on there. Whatever the end of your period is, put that down. Cut it in half. That's pi. Cut each portion in half. So half of pi is pi over 2. That makes sense? That half of it divided by 2. If you want to find the other half of it, add whatever that is to whatever that is. So pi over 2, and now I'm saying whatever that is and not specifically pi because it changes on your period. But find the end of your period, find half of it. Cut this first half in half again, that's pi over 2. And then add this to this. So pi over 2 plus 2 pi over 2 is 3 pi over 2. Pi over 2 plus 1 pi, that's 2 pi over 2, is 3 pi over 2. So number 1, we find our period, great. We've determined that it's 2 pi, we put that down, we cut it in half. Cut it in half again, why? Because important things happen at the ends, the center, and the quarters. Cut it in half again, and then add these two together. It will give you whatever that middle, or sorry, the second quarter is. I guess it's third quarter. But whatever this quarter is, you can always find it by adding the quarter plus the half will give you the 3/4. That's exactly how fractions work. Now, identify what trig function you're working with. So we've done the period. We don't have a vertical shift. We look here, there's nothing added or subtracted. Right now, if we would have had that, we would have said, okay, here's my period. I'd shift this up or down. I'd redraw like an x-axis and then redo my period on top of that. So I draw that right there. And since we don't have that, we're gonna move on a little bit and say, okay, we've done this. We don't have a vertical shift. Mark your x-intercepts. This is what was really important. I spent probably 10 minutes talking about last video, probably more than that, is you need to know what your x-intercepts do for sine and for cosine. For sine, our x-intercepts are at the ends and center of your period. Notice what I'm not saying. I'm not saying 0, pi, and 2 pi. Why not? Because our period can change. Our period can phase shift. And so I'm saying ends and center. In your head, I need you to know that sine has x-intercepts at ends and center of period. So I'm going to mark that down. So ends and center. So done the period, wrote the period. Broke it into quarters, got that. You can also do that mathematically too. Just divide by 2, divide by 4, divide by 3/4, and you can figure out what those quarters are as well. I've done that. I've identified I don't have a vertical shift at all. I know that with sine, I'm dealing with ends and center for x-intercepts. And now, the quarters that you have for sine, or the ends and center for cosine, whatever you have not put a point on, here and here, those become your key points. So if we have a visual of how sine looks in our head, our x-intercepts are ends and center, and our peak is at pi over 2, 1, and 3 pi over 2, -1. That should have been familiar from the last video. We know that pi over 2, 1, and 3 pi over 2, -1. What if you forget that? Look at your unit circle and think about the quarter of a circle. Now, I'm not really saying quarter of the period here. Pi over 2, I'm saying quarter of the circle and 3/4 of the circle. That's the first quarter and third quarter. This is what it will be, is pi over 2, 1, and pi over 2, -1. Those key points allow you to multiply by whatever that number is. That's going to stretch this or compress it and possibly reflect it. So again, period, got it. We cut it up, got it. Ends and center for sine, for x-intercepts, we got it. What we don't have points for are your quarters for sine. So create some key points. Key points are things that allow us to manipulate the look. That's pi over 2, 1, and 3 pi over 2, -1. That was on our original graph. And those are always going to be the cases for sine. You'll have your first quarter, comma 1, your third quarter, comma -1. And then multiply it by whatever your amplitude is, but not with the absolute value. Whatever your A is, positive or negative, it will allow you to reflect it. So in our case, times 3 and times 3. Now, this should be really familiar if you've had me before in these videos. You should understand that what that 3 does, that 3 is a factor for the output. So think about that. When you plug in a number to here, you'd have sine of whatever that is. Sine of this is going to give you some sort of an output. This output gets multiplied by 3. So use the 3 to multiply the output, not the input. There's nothing here that's being multiplied right now. 1 is being multiplied right now, not 3. This factor multiplies the output of sine. This factor multiplies the output of sine. And this is how we affect our key points. So pi over 2, your inputs will never ever change. Your outputs will change. 1 times 3 is 3. -1 times 3 is -3. Hopefully you're seeing that this is all we're doing is multiplying our output times our A. Notice something, how if that were negative, this would become -3 and it would reflect it. Instead of going up, it'd go down. It's a great way to graph this. And we're just going to plot our 2 key points. So for sine, you'll only have 2 because only the peaks and valleys happen at the quarters. So pi over 2 comma 3. Hey, we already have that marked down. That's great. We did that so that we could even get our key points in the first place. So pi over 2 comma 3 and 3 pi over 2 comma -3. Now really, I've squished my scale. So here's how our graph looks. So our graph is this sine function. It goes forever. We've just graphed one period. What if you had to graph more than one cycle or more than one period? Well, you would just double. You double this. So if you had to do 2 cycles of this, take your 2 pi and double it. What would you get? 4 pi. And then add 2 pi to every one of these, and you'll get a new period. Notice you're not doubling everything because pi over 2 times 2 is well, that would just be pi. So you're not doubling that. You're doubling your period, that's 4 pi, then adding 2 pi. Pi over 2 plus 2 pi will give you the next quarter of the next cycle. Do that. Now I'm going to superimpose something. I'm going to superimpose what would be the original sine function. You're going to see something here. That is exactly what a vertical stretch will do. It'll take your original dotted line sine function and grow it. So it increases what's called the amplitude. So the amplitude is this value of 3, how high it gets above the x-axis and below the x-axis in terms of its absolute value. That is what the amplitude relates to. So I hope I've made it make sense to you. I hope you understand that the way that I'm trying to show you here is a way that I've already given you for transformations. We just have something new in terms of this repeatedness of your trig function, of this every 2 pi for the period idea. So I hope it makes sense. I hope that you're really seeing what's going on, the reason why I'm having you do these steps in these orders. Let's practice a couple more of them. All right, let's talk about y equals -4 cosine x. I'm going to start moving a little bit quicker here, talking about our period pretty quick, talking about where our x-intercepts are and our key points as relating to the quarters or the end and center for whatever trig function we're trying to define. So y equals -4 cosine x. The very first thing we do with every trig function is identify what our period is and maybe what it changes to if we're multiplying the input by anything. So for cosine, our period is originally 2 pi. Remember, sine, cosine, secant, cosecant are going to have periods of 2 pi. Tangent doesn't, has a period of pi. So identify whatever your period is originally, divided by whatever number is being multiplied by your input. I say that specifically because for a phase shift, you might have to factor something out first. Here, we just divide by 1, and we get that our period is 2 pi. Draw that first. Draw your period, cut it in half. Cut it in half again. Add these two, it'll give you your third quarter. So we've identified our period, we've shown our period, we've shown our quarters of our period. So first quarter, second quarter, third quarter, fourth quarter, that's going to be our entire period. After that, what we're going to do is identify what sort of a vertical shift we have, if we have any. That will always be added or subtracted. Adding or subtracting, think about why that would happen. If I plug a number in, cosine of that number is going to give me an output. This would multiply that output, but then something added or subtracted would literally add or subtract to or from the output. That's a vertical idea. That's a vertical shift whenever we have something added or subtracted. Now we don't have that here, but we would show it. We'd show it as an adjustment of our x-axis, sort of like a new x-axis, moving up or moving down. A phase shift would also happen here, and we would shift to the right or to the left at this point and show that with a y-axis movement. So we've shown our period, we got that. We don't have a vertical shift. What we're going to do now is identify that for cosine, our x-intercepts happen not at the ends and center like sine, but at the quarters. What that means is that if these are x-intercepts, our peaks and valleys, our key points, are going to be at the ends and center of our period. Notice I'm not saying 1, 0, and pi and 2 pi. I'm saying whatever your periods change to, take the ends and the center. You've already marked it down. That's why we do it first, so that you can identify your key points. I hope that makes sense to you, that if you don't show your period first, you might have a very hard time finding the ends and the center if your period's not just a standard 2 pi. So I'm going to show that my key points are 0, pi and 2 pi, and it relates to our original cosine. We're gonna take these key points and we're gonna adjust them by multiplying by -4, but I want to write them out first. Remember, our key points from our original cosine function we got in the last video are, you'd have 0, 1, pi, -1, or first the first 0 is 1, and then -1, and then 1. If you forget that, look at your unit circle. The original cosine. Do the original one, then change it. So if you look at your unit circle and you say, hey, cosine of 0 is 0, 1, that's not right. And cosine of pi is -1, and cosine of 2 pi is back to 1. Those are your originals. Now, what would happen if you didn't have 0, pi, and 2 pi? You'd get the same numbers here. It's just manipulating your how much you're squishing that period. So you go, okay, the first point would give me 1, second point, that's half a rotation, gives me -1 or half a period, and then the third one is a full rotation, gives me back to whatever this is. So we've completed that period. So I'm going to take this, I'm going to say, if these are my key points, then what I'm going to do is understand that I can multiply those outputs times -4. So cosine of some sort of input is going to give us an output that gets multiplied by -4. What's it going to do? Well, it's going to stretch it, and it's going to change the sign. It's going to reflect it. So take that and multiply your outputs, not your inputs, but your outputs. So 0, cool, pi, awesome, 2 pi, got it. 1 times -4 and -1 times -4 and 1 times -4 give us a stretched and reflected output. These are the points that you need to graph on top of that period. So we're going to show that right now. So let's plot it. Because we've used our appropriate inputs as related to our period, we know that these should really be points on that graph. So 0, -4 says I'm going to be right down here. Pi, 4, I'm going to be right up here. 2 pi, -4, I'm going to be right down here. if you can picture the original cosine function, this is reflected and it's stretched. I'm going to draw it for you in just a second. It's kind of ugly, but that's about how that graph should look. Now, what would the original look like? Remember, this scale is a little off because I'm really squishing this graph. But the original cosine function looks about like that. So here's the original cosine as it relates to a height of 1 and -1. Look just like this. Nice smooth curve. This is reflected and stretched out. That's exactly how I would like you to graph these things. Are there other ways to do it? Yes, but none that I've seen work as cohesively, especially when we get to phase shifting. Phase shifting can really throw students for a loop. And so I want to make sure that we're really good at this before we get there, because this technique works really well, especially with the key points that we have. So what I'm going to do is give you a couple, 4 or 5 more examples of increasing difficulty to the point where when we see sine and cosine, at least, we're really good at dealing with it. Then we'll transition to tangent and cotangent and deal with some of this. And then finally secant and cosecant. They're very awkward graphs. Then we will get into our phase shifting. All right, we're ready for another 2. So let's take a look at sine of 3x. And let's go through the process of graphing this thing just like those steps talk about. Number one thing, whenever you are doing this, we are going to find the period of our trig function first, no matter what. So we might have to manipulate the argument of that trig function a little bit if we have some sort of a phase shift. We might have to factor that, but we don't here. We have no sort of a phase shift that would be added or subtracted inside the parentheses. I'm trying to get you ready for that in many more videos from now, but start prefacing that in your head. So we're going to take a look at this and go, okay, what are we seeing? We're seeing sine, and we're seeing the inside of our function, we have 3x. That 3 affects the period. So in our heads, we need to understand that sine has a period of 2 pi. But we have to divide that by whatever that number is, that coefficient of our x. That's going to start cutting or lengthening our period. What's that do? That's going to create this horizontal compression or horizontal stretch. That's what happens here. So this is take your period, sine has a period of 2 pi, cut it in 3. Well, that's just really shrunk this horizontally. That's going to make it very narrow. Now, I'm not going to show that as narrow as it should be, but that period says you're going to have a period of 2 pi over 3. Stop right there. Don't do anything else. Plot that on your x-axis. So I've plotted 2 pi over 3. That's my period. Go through the same thing. Cut that in half. So wait a minute. What happens if you cut 2 pi over 3 in half? 2 pi over 3 divided by 2, or cut in half, is 2 pi over 6, or 2 pi over 3 times 2. Those 2's cancel. You're going to get pi over 3. Now, cut pi over 3 in half. So you found period, half your period. Now find the first quarter. So pi over 3 divided by 2, cut in half, is pi over 6. How you can always divide fractions by 2 is multiply their denominator. So pi over 3 cut in half is pi over 3 times 2. That's pi over 6. Now, if you didn't catch it in last example, catch it here. Sometimes it's very difficult to find that for students. I've seen teachers tell them to average these two, which you certainly can, but it's very difficult. You can say, hey, pi over, not very, but more difficult than it has to be. Pi over 3 plus 2 pi over 3 divided by 2 is going to give you whatever that is, but it's a little bit easier to think about, hey, if that's 1/4 and that's a half of your period, 1/4 plus a half is 3/4. That's what that is. So just add those two. It will give you whatever that third quarter is. So pi over 6 plus pi over 3. Use your calculator. 1/6 plus 1/3 if you want to. It doesn't really matter. But pi over 6 plus 2 pi over 6, that's pi over 3, is going to be 3 pi over 6. That's going to be pi over 2. So now that we've got our period all lined out, we know exactly what the important points are for this graph. We know that this is dealing with sine. We know how sine looks. We know specifically that sine has x-intercepts at the ends and at the center. Mark 'em. I hope right now you're realizing why we do the period first, because everything revolves around that, like literally. Everything revolves around it. So if we have our period and we know that sine has x-intercepts at ends and center, we know exactly where our x-intercepts are. That's very, very nice. We also would have done a vertical shift now had we had it, but we don't. So we've said period, no vertical shift. Sine says x-intercepts, ends and center, we got it. The rest of the points, the rest of these values, the things that you don't have x-intercepts on, become the x-coordinates of your key points. So notice with your key points, I know in the last video I had specific key points. Those changed. The idea was for sine, your really important key points happen at the quarters. Whatever the quarter your periods are. That's pi over 6 and pi over 2 right now. Those are the x-intercepts of your, or x-coordinates of your key points. Now think back to what sine does. Sine has x-intercepts at ends and center. It has peaks at the quarters. First quarter is 1. Second quarter is negative, or sorry, third quarter is -1. So I'm going to put that, I know that sine has a 1 at its first quarter originally, and -1 at its third quarter. This is what we want to multiply by whatever's out front. Now we don't have anything right now, but we will in just a while. So we'd say these are our key points. First quarter, I'm not saying pi over 6 on purpose. I'm not saying pi over 6 on purpose. First quarter, 1. Third quarter, -1. This is what you'd multiply times whatever's there. In that case, that's just 1. That's not going to move this. It's not going to stretch it, not going to reflect it. So we're going to plot those. Pi over 6, comma 1, or first quarter, comma 1. Third quarter, -1. And we have a sine function that's been horizontally compressed. If we shorten that period, if we cut it up, it's going to compress that sine function. It'll happen more regularly. I hope that makes sense to you. I hope that you're seeing the utility in how I'm graphing these for you. One thing I do want to say before we get here is what would happen if instead of sine of 3x, you had sine of -3x, or you can think of this, y equals cosine of -2x, and you go, I don't like that. Neither do I. There is never a time when you should have a period with a negative in it. You go, wait a minute. Wouldn't you divide 2 pi by -3? Well, you would, if you were kind of doing it wrong. Here's the deal. Because sine and cosine are odd and even functions, you can always change the argument, if it's negative, into a positive by using the fact that this is odd or even. Remember what odd functions do. Odd functions say, opposite inputs, opposite outputs. What that means for sine, because it's an odd function, is that if you have sine of a negative inside of your function, you could write this as negative sine of 3x. Odd functions say opposite inputs, opposite outputs. That's odd, and that's what this would do. Notice what you cannot do. You cannot pull a -3 out. You're not actually factoring a negative out. Get this, man, this is a big misconception for students. You're not factoring out a negative here. You're not just pulling it out. You're using the fact it's an odd function. You're using this. That's what you're doing. It's not magic. It's not like, well, sine has a magic where you can pull out a negative, but cosine, no magic happens. Let's say you can't pull out a negative. That's not it at all. What it is because sine is odd, it follows this. It says if you have a negative in the argument, you can put a negative in front of your function and change the sign of your input. That's what this is saying, and that's why it works. You're not pulling out a negative. You certainly can't pull out a 3. What would it look like? Well, would you still have the same period? Yes. Now that you've changed this to be more appropriate, you have a period that's the same. It looks just like that. You have key points that are the same, except that with this negative, here's what would happen. This negative, it's -1, would now multiply your key points. Notice how that would work. You'd have a key point of quarter, comma 1, third quarter, comma -1, but you'd multiply those outputs and you'd get pi over 6 -1 and pi over 2 +1. First quarter, output gets multiplied by -1. Third quarter, output gets multiplied by -1, and it's going to reflect that. And so this graph would look like kind of pretty. Just a reflection, that's what that would do. Please understand, you cannot factor out anything inside of this. In order to change this, you need some sort of an identity. So in order to change your argument, you need some identities I haven't taught you yet and identities that I have. One of them is that sine's an odd function. Negatives can change the sign of your function along with the sign of your input. Now, what would cosine do? Well, cosine of -2x, oh wait, cosine is an even function. Don't be taking 2 pi and divided by -2. That's crazy. We don't want a period of -pi. That's awful, right? That's really hard to think about. It's on the wrong side of the y-axis for us. We don't want to do that. So think about how cosine is even. Well, what do even functions do? Even functions, due to the symmetry about the y-axis, even functions say opposite inputs equal outputs. What that means is that cosine of -2x is exactly the same as cosine of +2x. Now, for a student who does not understand evenness, this looks like magic. It's like, wait a minute. Why do you factor out the negative here, but you don't there? You're not factoring the negative. Sine's odd, so opposite inputs give you opposite outputs. That's what this is saying. For cosine, cosine's even. Opposite inputs give you the same output. So in other words, cosine of a positive angle or opposite negative angle is giving you the same cosine. We studied that a long time ago, but this is how we deal with it. So at this point, we'd say, okay, now we're dealing with cosine of 2x. Let's talk about the period first. Period always takes the period of your trig function and divides it by whatever your coefficient of your x is, whatever's inside that parentheses. In this case, it's going to shrink it. So our period is pi. Draw the pi. So we put the period on our graph first. We cut it in half. We cut it in half again for the first quarter. This is going to make a lot of sense now what I was talking about here for the third quarter, but for the third quarter, hopefully you understand it's 1/4, 2/4, 3/4, and 4/4. But check it out. You can always get this by adding these two. 1/4 plus 1/2 is 3/4. Or likewise, pi over 4 plus pi over 2 is 3 pi over 4. That's the way I get the period every single time. Now, understand what's going on here. We don't have a vertical shift. We'd show it right now if we did. There'd be plus or a minus here to shift this up or down. We do not have that, but what we do have are the fact we have some x-intercepts due to the fact that this is cosine. Cosine always has x-intercepts at the quarters. So I'm going to put x-intercepts at the quarters that I just found. That's why we find that first. Cosine has key points wherever we don't have x-intercepts. So on your period where you don't have an x-intercept at 0, pi over 2, and pi. If you're starting to build something in your head, you should be thinking that, hey, sine is always going to have 2 key points and cosine's always going to have 3. That's true. sine always has three x-intercepts, and cosine always has 2. Because we have 5 key points all the time, 3 of which are x-intercepts in sine, that gives us 2 peaks, and then for cosine, 2 of which are x-intercepts, that gives us 3, which are peaks. So we're going to draw that. So here's what we need to know about cosine. You need to have a mental picture and understand that cosine has a peak at the first, so right before we even start, has a peak when we start, has a peak in the middle, and it has a peak at the end. And it goes 1, -1, and 1 originally. So we're going to write that down. So where we start has a peak of 1. In the center has a peak of -1, maybe a valley. At the end has a peak of 1. So notice what I'm not doing. I'm not just saying 0, pi over 2, and pi. I'm saying at the first part, the beginning of the end, we have a peak of 1, and in the center we have a peak of -1, or a valley at -1, a local minimum. Then what we would do is we'd take a look at that, and we'd see if we need to multiply it by anything. Because we don't have a change in amplitude, we do not reflect this. There's nothing there besides 1. We don't multiply anything here. If we had, we'd multiply these outputs. So we're going to go to our graph. We're going to put these right on our graph. The values are already there on our x-axis. We should fill out our points. So 0, 1. Pi over 2, -1. That's right in the center. And then pi 1. That's at the end. And we get a cosine graph. This is just shortened this way. And so this would repeat with more frequency, is what we call that. So this would go faster and faster and faster, but can you see it's just a cosine function that's shrunk? I hope it's making sense. I'm going to start building this in difficulty. We're going to talk about how to adjust both your period and amplitude in just a second. We'll talk also about how to put in a vertical shift there. All right, let's get after it. So we got a couple more. How about y equals negative sine of, x over 8. That's weird. That's like 1/8. And you might see it written that way. You might see y equals -2 sine 1/8 x or something like that. That's fine. Here's what we're going to do. We're going to find our period and vertical shift first. We're going to graph those two things. So here we see a change in our period, but not a vertical shift. How we always deal with the period, we talk about it first, is take the original period, whatever trig function you're dealing with, in this case sine, that's 2 pi. Divide by whatever's being multiplied by x. Keep in mind, this fraction here is 1/8. You have to divide by 1/8 here. So 2 pi divided by 1/8 is going to give you 16 pi. Remember, you can multiply by the reciprocal, and you're going to get 16 pi. Now, I'm going to start having you think about something a little bit differently. If we would have a vertical shift, what we're going to do is graph these in conjunction with one another. So I don't have a vertical shift here, but I do here. And so here's what we would normally do. We'd show our vertical shift, and then we treat that like a new x-axis, and we put our period on that. So since I'm not shifting right now, I'm going to put my period on my x-axis. 16 pi, this is going to be a really stretched out period, so a really stretched out graph of sine. Let's find half of that. That's really convenient. Let's find half of that. In between here, remember, you can always add these two to find the third quarter. That's 12 pi. So we've gone ahead, we've looked at our period, we've looked at our vertical shift. You typically deal with those in conjunction with one another. I'm going to show you that on this example. We've put our period down. That's fantastic. Now we're going to take a look at what trig function we're dealing with. We always do this in this order. So got it and got it. These go together. At mark x-intercepts. So trig function is sine. Our x-intercepts are at the center and at the ends. So center and ends for sine. Whatever's not an x-intercept is going to be a key point for you. So I'm going to put 4 and 12 pi. We need to have a mental picture of sine in our head. We understand that for sine, at the first quarter, we're 1, and at the third quarter, we're -1. You can see it on a unit circle. First quarter of the circle, sine is 1. Third quarter of the circle, sine's -1. That is what this is referring to. It's just stretching this out a bit. So 1 and -1. So we have found the period and the vertical shift. We marked our x-intercepts. We have our key points based on our quarters, the things that aren't x-intercepts in this case. And now we know that we'd have normally we'd have a peak at 1 and -1. However, our key points get affected by reflections and by vertical stretches and compressions. So we're going to take whatever this is and multiply our outputs, our key points outputs by that. So 2 times -1 is -2. -2 times -1 is +2. So what this has done is this has taken and lengthened our period. That's a horizontal stretch. This has taken our key points, the outputs, and made them change sign. That's a reflection, and grown them by a factor of 2. That's a stretch. So this is a horizontal stretch. That's the period. It's a vertical reflection and a vertical stretch out of that. And that's what's happening here. So because we know at the first quarter we normally get 1, and at the third quarter we normally get -1 for sine, we're now multiplying by -2 and reflecting that and stretching it. We just have to plot these now. So 4 pi -2, 12 pi +2. And we get this reflected sine function like we expected. And that's about how that would look. To get a real clear picture of what's actually going on, please remember that the normal period for sine is 2 pi. Wait a minute, that's like right here. So normally, here's how this graph would look if you want to see it superimposed a little bit. That's about how that would look. So this has been, I'd go down a little bit more right there. But this has been really stretched out and quite a bit vertically stretched as well. So that's the original sine function. And then this is the reflected, stretched horizontally, and stretched vertically sine function. I hope it's making sense. I hope you're seeing the interaction of the key points, especially in this graph. It's quite important. Okay, let's move on to y equals 3 times cosine of 4x plus 1. The first thing we do with any trig function is figure out the period, yes, but we also want to consider any vertical shifts. I'm going to show you how that works here. So our period says, look at your trig function, it's cosine. Cosine has normally a period of 2 pi, but now we're dividing that by 4, so that's going to be pi over 2. This also has a vertical shift right there. Think about what would happen. You'd plug in a number, find cosine of the number, that's an output. 3 times that, that's an output, and then you add 1. Where are you adding 1? Not to the input, you're adding 1 to the output. So this is going to affect the output here. This is a vertical shift, up 1. So there's a slight change in what we're going to do. Instead of just putting our period on our x-axis, here's the thought. If we're going to shift this up 1, let's sort of pretend the x-axis shifts up 1. So we're going to make a dotted line, a horizontal dotted line right here, and we're going to put our period on that dotted line. You can put it in both places if you'd like, but it really helps to put it on your shifted axis. Now, is the x-axis really moving? No, not really, but we're going to use that as a graphic organizer on which to put our key points. It's how the key points work, is on the shifted versions of your axes. So I'm going to draw that horizontal line. What that represents is our entire function is shifting up 1 unit. Every output at every point shifting up 1 unit. What we're going to do is graph our period on that. So we're going to do that right now. You can also put it on your x-axis. I just find it very, very helpful to put on this line, especially when it's way above or way below. So pi over 2 is our period. Half of that's pi over 4. Half of that's pi over 8. If I add those two things together, let's see, pi over 8 plus 2 pi over 8, that's 3 pi over 8. Now this is key. When we talk about cosine having x-intercepts at the quarters, keep in mind what we're doing. Because we shifted this up 1, this is why we draw this dotted line. This is why I'm putting the period on that dotted line. I know it's not really there. I know that x-axis is right here, and that's totally fine. But because I've done that, I now know that not only does this function shift, but the x-intercepts also shift. And so we can plot our x-intercepts at the quarters, but they've got to be in relation to where you just shifted. What that means is that our x-intercepts are not really x-intercepts anymore. What they are places where we would now intersect this horizontal line at y equals 1. So that's at the quarters. So remember, cosine, x-intercepts at quarters. What that means is cosine, where we would have some key points here are at pi over 8, 1, 3 pi over 8, 1, we're sort of pretending it's an x-axis, and we'd get two very important key points here. No, they're not x-intercepts anymore. Hopefully that makes sense. You don't just magically move your x-axis. It's just a graphic organizer for you to create a very good-looking graph with minimal work. But those points would be pi over 8, 1 and 3 pi over 8, 1. We're treating them like x-intercepts because we're shifting. Everything else, so the ends in the center, become your key points. So I'm going to put down 0. Here's 0. And so x equals 0, and pi over 4 and pi over 2. We also need to understand what cosine does. Cosine has peaks of 1 at the ends and -1 in the center. Those are our key points as it would relate to a cosine that's been sort of squished to a quarter of the normal period. Now we're going to say, hey, those things can be multiplied by whatever number's here. That factor out in front multiplies your outputs, so allow it to do so. So 3 times all of these outputs. So we'd get 0, 3, and we get -1 times 3 here. We get 1 times 3 here. So pi over 4, -3, pi over 2, comma 3. Those are our new key points. We're going to plot them in relation to our shifted x-axis. So there's a lot going on here. Here's what we've done. We've taken a look and said, hey, our period has shrunk. That's a horizontal compression. We've shifted up 1. That's a vertical shift of 1. So that's acts like our x-axis. We've recognized that for cosine, x-intercepts are at the quarters. So it acts like x-intercepts on that shifted version. We said, all right, our key points will happen at ends and center for cosine. We've written them down. We know that peaks are at the beginning and end and of +1 and -1 in the center. We've written that down. We've adjusted with a vertical stretch here. So we've had a horizontal compression, a vertical shift, and a vertical stretch of 3, and that we've shown that. Now we're going to plot these key points, but please get this is the biggest deal. Because you shifted that, these key points relate to this as acting as your x-axis. It's not, I know it's not really there, but it acts like it. And so we plot these points in relation to this thing right here. What that means is that 0, 3, this would act like 0, 0. I know it's not there, but it acts like it. This would be 0, 1, 2, 3. This would be acting like 0, 3. If you've seen my previous graphing, that makes sense. Look, I know that point's actually 0, 4. Like, everybody realizes that. This is just a very good way to get an accurate graph without having to plug in a ton of points. It's the best way I've come up to deal with it so that students actually understand what they're doing. How about pi over 4, -3? Here's pi over 4. We're going to treat this like the place from where you are putting your key points. So pi over 4, comma -3 is 1, 2, 3, right here. Pi over 2, comma 3, this acts like your x-axis. So pi over 2, comma 3 is right about there. Can you see that it's a cosine that's been shifted, shrunk this way, grown this way? For the last time, yes, everybody realizes that you don't actually have x-intercepts here and here. It's just a graphic organizer to help you graph it. I hope I've made the point that your key point, I know I have, but that your key points are in relation to where you shift to, both up and down. And when we get to phase shifting, left and right as well. That's why we do these in a certain order. So period, yes, but a vertical shift and next, I have several videos from now, and a horizontal shift, they all work together. So you put your period after you have done your shifting, put them on that new x-axis, that new x-axis that you have. So I hope that makes sense. We're going to come back with like 2 more, maybe a special case, and we'll be done. Okay, kind of some awkward ones. They look a little weird, like, wait a minute, what's that doing in there? How are we going to have pies and something that you plug in pies to? It's actually going to be a little bit easier, but you have to see it a couple times. So I'm going to walk you through this one. I'm going to go very quickly through this one. You need to do this on your own. So let's take a look at our 4 sine pi over 2x minus 2. And the first thing I really need you to understand is there is an extreme difference whether this parentheses ends here or here. If you have something added or subtracted outside of your function, that's a vertical shift up or down, where minus means down. If this had been inside your parentheses, where this wasn't here, you would have to factor out a pi over 2, and that would become what's called a phase shift, left and right. Oh, you should remember that. You should remember that anything added or subtracted inside your function is left or right, but it has to be in a certain form, and it's opposite of what you want it to be. Do you remember that? I hope you remember that. I hope that you remember that subtracting is to the right and adding is to the left inside of a function as far as our horizontal shifts, and therefore phase shifts are concerned. So let's get back to it. There's a few things going on we need to really understand. The first one is the period. The period always says take the period of your original trig function, or the original period of your trig function, 2 pi, and divide it by whatever coefficient is in front of your x. Wait a minute. 2 pi divided by pi over 2, well, the pi's are going to cancel, and we would get, well, if we reciprocate and multiply, we get 2 pi times 2 over pi. The 2's give you 4, the pi's cancel, you are going to get 4 here. Wait a minute, can you have a period of 4? Yeah, it's actually a little bit easier to deal with. Just put 4 on your graph. Now, we're not going to do it now, though, because we also have a vertical shift. So that minus 2 says you are going to shift down 2. And so we're going to show that. We're going to put these together. In general, we show our vertical shift and horizontal shift, a phase shift first, and put our period in relationship to the new shifted axis. So we've done our vertical shift of down 2. We know our period's 4, so let's go ahead and put the period on our, I'm going to put it on the x-axis, but I'm going to show all of our marks on my shifted axis. If we do this to scale, here's 2, that'd be about 4. Half of that's 2, a quarter of that's 1, and 3/4 is 3. That's kind of nice. 1, 2, and 3. So we've gone ahead and we've done our vertical shift. We've done our period. We now know that we're dealing with sine. And so sine has x-intercepts at the end and center. What that refers to now, because we shifted this, is our x-intercepts change to just some key points that interact with that shifted version of our x-axis. Ends and center. That leaves us with 2 key points based on our quarters, 1 and 3. Remember what sine does. Sine originally peaks at the first quarter at 1 and at the third quarter at -1. This is why it was so important for you to remember that, yes, those key points on the original sine function are great, but the way they refer to is first quarter and third quarter. Peak at 1, peak at -1, or valley, I suppose, at -1. That's what we have here. First quarter +1, third quarter -1. Then we allow this to affect our outputs. So what this has done, this has taken and grown our period, actually, because shrunk our period, because the period was originally 2 pi. This is smaller than that. This is smaller than 2 times pi. This is 4. So it's horizontally compressed us. This has shifted us down to, this is going to vertically stretch us. So we have our key points, 1, 1, yes, but now 1 comma 4 times 1 is 4. And likewise, 3 comma -4. Plot these in relation to your shifted axis and your quarters that you put down. So 1 comma 4 starts from here. 1 comma 4 would be 1 comma 1, 2, 3, 4. 3 comma -4 would be 3 comma 1, 2, 3, 4. And we get a sine or sinusoidal function out of this thing. What if you had to keep going? Could you do this for another cycle or another period? All we would do is double this. So double this period, you get 8. Add whatever this number is to each of these things, and you will get the filled in version of that. So 1 plus 4 is 5. That's it's called the next first quarter. 2 plus 4 is 6. That's in the center. 3 plus 4 is 7. And you would get another ability to put down your x-intercepts at the ends in the center. Your key points will just shift over. So remember, this is why we talk about first quarter being 1, or first quarter being 4, third quarter being -4, so that you can just move it. So now here's your first quarter. First quarter is 5. So 5 comma 4, 1, 2, 3, 4. Third quarter -4, that's 1, 2, 3, 4. And we get another cycle out of it. You can keep going forever and ever and ever like that. Again, this is the last time I'm going to say this, probably not, but the last time I'm going to say this is, yes, the key points are not actually, 1, 4 is not on your graph, all right? 1 comma 2 is on your graph. It's just plotted in relation to your shifted axes so that you can do it, so that it's easy. You're not plugging in points all the time. I hope the technique makes sense to you. I hope that you're understanding it. I hope that you like it. I've seen it work very, very well. When a student understands it, then they never make mistakes on it, or very rarely. Okay, I told you I was going to go quickly through it. We have cosine here. Cosine has a period of 2 pi. If we divide by pi over 4, then that's going to give us a period of 8. Now we're going to graph that in just a bit, that period, but we're also identifying that that is up 2. So I'm going to take and I'm going to make a vertical shift up 2. Now because we've done that, we can put our period of 8, notice reciprocate, multiply, you're going to get 8. Put our period of 8 on our x-axis and the shifted version. Now cut it in half. Cut it in half again, that's our first quarter. Add these two, that's your third quarter. So remember what cosine does. Cosine peaks at the first quarter, at the beginning and at the end, and right in the middle. So at the 0, if you will, at the halfway point, and at the end. 1's at the beginning and end, -1 in the center. Has x-intercept at the quarters. So x-intercepts now shift. What that leaves us with are 3 key points, 0, 4, and 8, the centers and the ends. We also remember with cosine that originally, before we start shifting it, before we start manipulating it, before we start vertically stretching and reflecting it, that those ends would have a 1 and the center would have a value of -1. Those, however, get changed. They get transformed by that number. That number, that output, that factor affects the outputs of your function. So it's going to take those outputs, it's going to multiply by -3. So we've seen affect the period, got it. Shift up 2, got it. Draw them together. After that, we have our key points at the center and at the ends for cosine. No problem with x-intercepts at the quarters. We got that. That's what cosine does. You need to remember that. Because we know that the ends and the center have a peak of 1 and 1 and -1 respectively, this is a multiplier. That factor multiplies the outputs. It grows and reflects things. And so we've done that. As long as we plot these key points from our shifted version on our period, we're going to be fine. So this says where you begin. Notice I'm not saying just 0, just where you begin. That's going to be affected on a phase shift. Where you begin is at 0, -3. So here's 0, 1, 2, 3. 4, 3. That's the center, and then 3. Here's the center of the period, comma 3. And here's 8, -3. That's the end of the period, -3. Obviously, the point on the graph is not 8, -3, it's 8, -1, but that's because we shifted up 2 units. The point here is to use it in relationship, and you're going to get a very nice graph. So what's happened here? We have, let's see, stretched out our period, so horizontal stretch. We've shifted up 2, so vertical stretch of 2. We have reflected this. You can see it's not like this, it's like this now. And we've vertically stretched it. That's 4 transformations. And that's 1 period worth of this particular cosine function. Man, I hope I'm making it make sense. I hope that at this point, like, yes, I get this. Please stop with the examples. Well, I'm not gonna. I'm gonna give you one more, going in reverse, and then we're gonna be done with it. Okay, so what if you have to go backwards? What if you have to create a function from an amplitude or a period, or even from a graph of a function? We'll talk about that. I'm not gonna do one for you. They're not as super common, but I will talk about how to do that. So if you have a period, could you write a function from it? If you have an amplitude, could you give it a number in front? Now notice this won't give you reflection, but you could talk about it. As far as the period goes, we know that if the period is the period of your original function, so you need to know whether you're getting a sine or a cosine out of it. In this case, we want a sine. We need to know what our original period is, and that is divided by whatever your omega is. So wait a second. If you have a period of 4 pi, then what this translates to is 4 pi, hey, that's our period, equals, this is what our period always is. So if you have 4 pi equal to 2 pi over omega, can you solve for omega? Yeah, we'd multiply both sides by omega and divide by 4 pi. Ultimately, what you do, just interchange these two things. That's going to give you omega equals 2 pi over 4 pi. Again, you can multiply both sides by omega divided by 4 pi, whatever you want. This is going to give you 1/2. In conjunction with what we know our amplitude to be, our amplitude is the absolute value of whatever our A is. So if we don't know whether we have a reflected graph or not, just consider it to be your A. And we can get a function from an amplitude and from whatever our period is. And that's about it. We just put our omega right there in front of your x and you're done. Now, weird question. What if your t wasn't 4 pi? What if it was just 2 or something? Well, we can do the same thing. We just understand that If we take our original period for our trig function, write the formula. Period is always pi over 2 divided by omega, and that's the number in front of x. So if we know that t is 2, then we can solve for omega. And omega would be pi. So we just change this to pi. And we would get sine of pi times x. And with the same amplitude, we would get that exact same function. I hope that makes sense to you on at least how to find whatever the argument of your trig function is from whatever your period is. We can do other things. I left this on the board for you just to say, hey, could you recognize that this is shifted up 2 units? Could you recognize that this is a reflected graph? Can you recognize that if we start and stop from 0 to 8, then you would have a t of 8. You can find your omega. This is a little bit more advanced, but it is something that you can do. Now that we understand how to graph from our trig functions, this should be doable to go backwards. I want you to do that sort of on your own. I've already shown you one example. You can get the same information from a graph. So I just wanted to mention that. I hope that this video has made sense. I hope that especially you understand how to relate your trig function and your period with your shifting, and then get your x-intercepts appropriate, ends and center for sine, quarters for cosine. Use the rest of what's not filled out, so rest that aren't your x-intercepts, to get key points, and then plot them in relation to your shifted axis. Hope that makes sense. I'll see you for another video when we start talking about what tangent looks like. Have a great day.